chapter 20 here, chemical kinetics. The first part of this up through 27 deals with just empirical analysis. We're just looking at the the curve, reaction curve, and then just trying to figure out the math involved in that to make predictions. And then from 28 on is a more theoretical analysis of why something would be zero, or not necessarily why, but description of how things are zero order, first order, second order in terms of reaction kinetics. So the rate, rates are always positive. And so if we're looking at rate of formation of iron 2, iron 2 is a product here. We're looking at the change in the iron 2 concentration over time. And so in this case, over a 38.5 second interval, 0.0010 moles per liter were produced. And so the rate is going to be this. It's 2.6 times 10⁻⁵ molar per second. And rates are going to have the units molar per time. And the time could be seconds, minutes, whatever, here. And so here, they're just calculating the time interval, T or delta T. Oftentimes in these kinetics, we use that interchangeably, delta T and T, because T is usually T final, and T initial is usually 0. So T final minus T initial is just T final. And so oftentimes delta T. But that's not always the case, so it's a good idea to know that T or delta T is usually the time interval, unless it's marked like T initial or T final, and we're looking at a specific time. All right, so this is the rate of formation of iron 2. But if you look at the stoichiometry of this, the stoichiometry is we're going to form iron, twice as fast as tin, because twice as much iron is produced in tin. And so if the rate of formation of iron is 2.6 times 10⁻⁵, then the rate of formation of tin, based on the stoichiometry of this reaction, has to be half of that, or 1.3 times 10⁻⁵. And that means the rate of consumption of iron 3 must be 2.6 times 10⁻⁵. And the rate of consumption of tin 2, we're going to consume tin at half the rate, and so that's going to be 1.3 times 10⁻⁵. And so we have to look at the stoichiometry, and then we can see what the rate is. But the problem with these rates is, does the rate change over time, or is the rate fixed? Because when we get a rate like this rate here was probably only valid at this concentration. And then it changes. And so here we see that tin, because of the stoichiometry, 2 irons for every tin, so tin must be half as fast, 1.3. The iron 3 plus, we're losing that. And so the rates are usually positive. And so what we say is that, we get a negative here because we're losing it, but we say the rate of disappearance. If we say disappearance, then we'll make it a positive. That is, we'll multiply a negative to change the sign, or just take the absolute value. And so all rates are going to be positive quantities. And what you have to do is you have to specify, is it consumption or is it production of that? And so based on the equation here, the rates of iron 3 and iron 2 are going to be the same. The rates of tin 2 and tin 4 will be the same. Those will be half that of the iron in this one instant of time. In general, the rates are going to be dependent on the coefficient here. A, B, little a, little b, GH. We usually don't worry about the products here, unless we're looking at the formation. Actually, we are looking at the formation here. So we have a generic rate of reaction, because what is the rate of reaction here? If we go back to this one, is the rate of reaction 1.3 or is the rate of reaction 2.6? Actually both are valid. We have to say the rate of reaction for iron is 2.6, the rate of reaction for tin is 1.3. But in general, you just want to know what the rate of the reaction is. And so what we do here is we come up with a generic rate of reaction. This generic rate of reaction, here it's given, is just normalized. And so per mole, let's say. And so what we'll do is we'll take 1 over A, 1 over B, 1 over G. So the rate of reaction is all the same throughout here. And so going back to our iron and tin here, the rate of reaction for the iron would be 1/2 because there's 2 irons, so it's 1 over little a. And the tin. And so the rate of reaction is based on 1.3 times 10⁻⁵. That would be the generic rate of reaction for this. All right, how do you measure the rates of reaction? Well, we already did measurement. For example, permanganate would be easy because permanganate is going to have a spectrum we can monitor in a visible spectrometer. Manganese 2 has a different color, distinctly different. This is light pink, it's almost colorless. This is deep purple. And so we can watch the spectrum. There are other ways to do it. Let's say you don't have a spectrometer. One way of doing it is monitoring the oxygen produced. So this is monitoring the oxygen produced. Although, the oxygen produced seems like kind of a hassle. But if you're doing hydrogen peroxide, then that's the only thing, because hydrogen peroxide is not colored. So it's difficult to see using a visible spectrometer. And so in this case, you have to do it based on the oxygen produced. Over here in this particular one, you're using permanganate in this redox reaction. Now, normally hydrogen peroxide is a oxidizer or reducer. Nobody knows? No, actually not a reducer, because hydrogen peroxide is in the top 5 of the oxidizers. In fact, in our chart, it's like actually, let's take a look at our chart. Here. If you look at our chart, fluorine is number 1. Hydrogen peroxide is number 4. It's in the top 5. I mean, at least you should know, some of the, although some of these aren't that common. S2O8, 2- isn't very common, but you should know the common ones. Fluorine, ozone, hydrogen peroxide, permanganate, very powerful oxidizers. How do you get that? This is just what they call memorization. And is it useful to memorize? Actually, it's critical to memorize stuff. Otherwise, you can't hold a conversation with people in science. You have to have a lot of little bits of knowledge memorized. But you acquire those over time. So the way you acquire this, you've got to acquire it rapidly because it's short. And just once in a while look at the chart. But anyway, decomposition of hydrogen peroxide. This one's going to be hard to monitor using a spectrometer. And then it's hard to monitor this, the hydrogen peroxide. So the easiest is to monitor the oxygen here. So we monitor the oxygen. But this is a very weird reaction. What stands out about this reaction here? This is a very weird reaction, the second one, because A lot of this memorization stuff takes time, and so this is why I'm not having the chemical reactions test until the final. It gives you the entire semester to pick up little bits here and there of chemical reactivity. But when I look at that, that really stands out as being a weird reaction. Why? Well, actually, the top one may stand out as a little bit weird too. The top one is called the disproportionation reaction. And on the chemical reactions homework, you might have seen this already. If you started, have you started? Has anyone started that chemical reactions homework sheet?
From the start of the semester?
From the start of the semester. I'm giving you an entire semester to do it, but don't wait until the night before the final to complete it. Oh, hope you don't wait until the night. I'm sure lots of people will. And that happens. I have that as bonus. The chemical equations as bonus, and so many people leave it blank. They get 0 out of all those bonus points, which are a lot. And if you need bonus points, then you should review this chemical equation stuff, chemical reaction stuff. It'll help. There's quite a few bonus points there. And well, the first one is called the disproportionation, because the funny thing is hydrogen peroxide is both the oxidizer and the reducer. The first one. The second one, why it's weird to me, is because permanganate's a powerful oxidizer, hydrogen peroxide is a powerful oxidizer. If you have 2 oxidizers, then nothing should happen, right? There's got to be an oxidizer and a reducer. So one of those is going to sacrifice as a reducer. Chem 1 sacrifices as a reducer, yes. Which one? Not permanganate, but I just said that hydrogen peroxide is a powerful oxidizer over here in the top 5. And typically when we think about hydrogen peroxide, which is number 4 on this chart, we think of powerful oxidizer. But also the other strange thing about this, and this is for people who actually looked at the chart, because a lot of people actually don't look at this chart, and a lot of people won't recognize that hydrogen peroxide is also a reducer. Let's see here. Its oxidation potential is minus 0.695 volts. Which means it's minus 0.695 volts worse than hydrogen, but it's still a decent reducer, like iron 2. Iron 2 is a decent reducer. Iodide, copper metal. It's worse than copper metal. I mean, it's not a great reducer, of course. It's hard to oxidize, but expected. And so these are things you could pick up if you kind of memorized a little bit of the reactivity of these things. But anyway, we monitor the hydrogen peroxide. This is kind of hard to measure. You measure it in some way. There are different ways to measure it. There's actually some spectroscopic ways of measuring it too. Even though we can't see the color, you can measure certain frequencies that it absorbs in the UV or wherever, in the infrared. Anyway, here's the decomposition of this. Okay, this is just simple. There's only one reactant. A goes to product. This is what we call single reactant. This is decomposition reaction. And so the only thing that's going to impact the rate is the decrease in the concentration of the reactant, hydrogen peroxide. Okay, eyeball this. Can you tell me 0, first, or second? Just eyeball the data without doing any calculations. Can you tell me? 0, first, or second? Is this a 0, first, or second order decay without graphing it? Just eyeballing the data. Can you tell me? I mean, it's A goes to product, so we have the choice of 3, 0, first, or second. This is, for me, this is easy. I can tell right off because of the pattern in the numbers here. I mean, you could see right away because the 3, 0, first, and second would give vastly different patterns in the numbers here. And what do I mean by vastly different? Well, what I'm looking at is half-life. If I'm looking at half-life, 0 is like this. If we cut it in half, it takes this long. If we cut it in half again, it takes half as long. So each successive half-life in this is like this, okay? So this is T1 half 1. This is going to be 1 half T1 half 1. Okay, and then that's going to be T1 half 2. This is going to be half of that. So each successive one is half as long. It has to be. Otherwise, we can't have a linear line like this. And so what I say is that it takes shorter amount of time to do that. That's 0. And then first, each successive half-life is exactly the same. Okay. And then second, each successive half-life doubles. And so the way I could do this is just this. You know, 232, we cut it in half, we're around 116, which is around here, maybe 1,000 seconds or something. And so let's go from 2, actually let's go from 2 to 1. From 2 to 1, how many seconds was that? This is just eyeball. From 2 to 1 to 1,000 seconds, right? And then 1 to about a half takes about what? So 1 to a half would be around 2,000 something. And so 2,000 something, that's going to be about 1,000 seconds. And so what it looks like to me is this looks like first order. This looks like first order because it's about 1,000 seconds. Look at this, 0.62 to 0.25. So if we went from 0.5 to 0.25, that would be half, right? How long would that take approximately? 1,000 seconds. You see, it just has to be ballpark 1,000 seconds because this option would be, each one would be double. So the first one would be 1,000 seconds, the next one would be 2,000 seconds. That for sure is not 2,000 seconds. And then this one would be half. And so if the first one were 1,000 seconds, the next one should be 500 seconds. And so since these are so dramatically different, then you could just eyeball this and see. This has got to be first order. And so this is first order. If that wasn't the only question, we would have had it answered. If this was like multiple choice, we'd be done with it. Instead, I suppose you could graph it. If we were to graph this, then you could see. We'll cut it in half. And so we'll just eyeball it. Cut it in half here, how long did it take? 1,100 seconds. We cut it in half again, how long did that take? Another 1,100 seconds, roughly. And so this is a first order decay or exponential decay. What's a black line represent? The black line represents a tangent at what time? The black line represents the tangent at time 0. That's the black line. So the slope of this line is the instantaneous rate at time 0. So it's very fast, decaying rapidly at time 0. But once we hit time 1600, it's slowed down quite a lot. And this is not 1600, is it? This would be around here, halfway between, 1400. Around 1400, this would be an instantaneous rate. The slope of this would be an instantaneous rate. And so these are to measure, these tangent lines are to measure the instantaneous rate versus the average rate. If we're looking at the average rate from time 0 to 1400, it would be a line that intersects these two. We get the slope there. The situation here is the rate is continually changing. Therefore, it's slowing down. Hydrogen peroxide decomposition starts off rapidly initially and then slows down. And you can see it here. What they did was they ended up calculating the slope, the instantaneous rate. You can see that the instantaneous, well actually this is not the instantaneous, this is the average rate. They're calculating the average rate between 0 and 400. The average rate is 15 here. And then it slows down between 400 and 800, it slows down to 10.5, etc. So the rate is slowing down. So this is here. These are the average rates, not the instantaneous rates, because they're actually using the data here to calculate delta Y, which is delta H2O2, and delta T, which is delta X. So we see the reaction rate slowing down. And then we talked about the tangent line. You know, that's the instantaneous rate versus the average rate. So this is a slide that says about the instantaneous rate, the slope of the tangent line versus the average rate, which is for time interval. Sorry. Okay, the rate of reaction when the reactants are first brought together is the initial rate. You know, the initial rate we said was either the slope of the tangent line at time. I had two definitions for the initial rate. What were they? The initial rate is the slope of the tangent line times 0, or when less than 95% reaction has occurred. Excuse me, when less than 5% reaction has occurred. All right, what we want to do is we want to see how the concentrations impact the rate. And this is called the rate law. The rate of reaction is equal to K, which is the rate constant. And the bigger the K, the faster the reaction. The smaller the K, the slower the reaction. Times A raised to the M. N is the order with respect to A, N is the order with respect to B. But you know, when we have multiple reactants here, we're concerned about the overall order of reaction. Overall order of reaction is just add up the individual orders. And the reaction is going to react based on the overall order of reaction. How do we get the rate law? The easiest way to get the rate law is the method of initial rates, which I already talked about the other day, and that is this. If we want to figure out, you know, M and N, what we do is we hold one constant, like the mercury, hold a constant 0.105, and then we double. If we double the oxalate here, what happens to the rate? And so take a look. Did the rate stay the same? No. Did the rate double? No. What happened to the rate? The rate actually quadrupled. We're going from 1.8 to 7.1. If the rate quadrupled, then this has got to be 2. It's got to be second order in oxalate. That is, if you double this, it's 2 squared, which quadruples. All right, then we hold the oxalate constant, let's say at 0.30, and then what we do is double the mercury. So from reaction 3 to reaction 2, we double the mercury. If we double the mercury, take a look at what happened to the rate. The rate went from 3.5 to 7.1, it doubled. Therefore, it's first order. That is, if you double it, it's 2 to the 1 power, first order. And so this is going to be first order in mercury, second order in oxalate. And so that means if you double both, let's say we double this one and double this one, what's the net impact? The net impact is going to be third order. That is, it's going to be 2 cubed, which is going to be 2 times 2 times 2 is 8-fold. We're going to get an 8-fold increase in the rate. See overall. So the effect of doubling the initial constant, 0 order, no effect. First order, it doubles. Second order, it quadruples. Third order, it increases 8-fold. This is third order overall. It's not third order of an individual reactant. Now, to figure out K's, if we know what M and N are, and we have these concentrations, we can calculate K pretty easily. Now K, it depends on the order of the reaction, because the rate of reaction is expressed in molar per time. And if this is molar, and this is molar squared, then K has to have the units molar to the -2, cancel that out, per minute. And so the K, the units on K vary depending on the overall order of the reaction. So again, units of K vary depending on the overall order of the reaction. So for 0 order reactions, K is just molar per minute, or molar is molar per second here. So the units of K. Here's the equations for this. The equations for this is the rate law. You know, K A to the 0th power. This should be 0 should be up here. Unfortunately, it's just K, which is constant. So we put on a constant slope. The integrated rate law for this is just here. The integrated rate law. This is the calculus bit. This calculus bit we're going to skip, and we're just going to go down to this blue box equation. This is just y equals mx plus b. You know, y is concentration A. Concentration A at time t is equal to minus k, which is the slope, times t, which is x. A is an intercept here. We could have gotten this equation easily without calculus. We don't need calculus for that because this is the concentration of A is y, m slope, x time, and the intercept is A0. So for 0 order, we don't really need calculus, but for first order, we do. First order reaction that we saw was hydrogen peroxide. This is all kind of reviewed from yesterday, rate of reaction. In this, the K is different, has a different unit because hydrogen peroxide is molarity, molar, and so K just needs to be per time, either per second or per minute or whatever. For hydrogen peroxide, it's going to be per second. Depends on how fast the reaction occurs. All right. Here we do this, and we came up with these equations the other day for first order decay. These equations allow us to calculate the time required or the concentration change, you know, a 95% reaction or whatever. We can do a plot, you know, natural log versus time comes out linear. And we can determine the slope of this line. Determining the slope of the line is different than determining the slope of the individual data points. We don't want to determine the slope of the individual data points because, you know, the data points fluctuate due to random error. You see here. And so by drawing the best fit line, called linear least squares or trend line like this, by drawing the best fit, we average out all those random errors. So we get the best slope for this. So the slope of the line is going to be the slope, the average slope of all these individual points here. And this is for determining the half-life. We can use this equation here. This is first order. We can use this equation to determine the half-life because the concentration of A at time t is 1/2 the original. And so A at time 0 cancels out, and we just get ln of 2, which is equal to minus kt 1/2. Well, ln of 2 is 0.693, so t 1/2, solving for time, is 0.693 over k. And so the half-life is just a constant over another constant. And so the half-life is constant here. Okay. And so half-life is constant for first order, but you know we just looked at 0 order. We could do the same thing for 0 order. what is the half-life for zero order and how does that differ? So let's calculate T1/2 for zero order. We do it just like we did it over here, and that is we use the integrated rate law, which we call, just the equation, mathematics of the curve here. A of time t is equal to minus kt plus a times 0. All right, and then a of time t, well, it's half of our original. This is the half-life. How long does it take to get to half the original? Which is equal to minus kt plus a times 0. And so what we're going to do is we're going to add a kt to both sides and then subtract 1/2 a0 from both sides. And so if we do that, we're left with 1/2 a0 over here. So this is T1/2 is equal to 1. Actually, let's just do it like this. So it's going to be a0 over 2k. And so the half-life depends on your starting concentration. And so each time we do, each time our starting concentration gets cut in half, the half-life will get cut in half. And so this half-life depends on the concentration over a zero order, but for this first order, it does not depend on the concentration. Now, we could do the same thing for second order. Okay, let's go to second order here. For second order, the equation is, these equations you don't have to memorize, but T1/2 for second order. So if we do T1/2 for second order, then the equation looks like this. 1 over a times t is equal to plus kt plus 1 over a times 0. And so why don't you determine T1/2 for me here? We could do, the same thing we could do. If there's 95% reaction, we could easily calculate. We don't need to know how much we started with, because how much we started with cancels out. But we could do 95% reaction, 80% reaction. 100% reaction is tough, because 100% reaction would require infinite time to complete in first and second order. As it approaches zero asymptotically. And so tell me what the equation is. Well, I get that T1/2 is equal to 1 over K A 0. Is that what you guys get? Okay. And that means if you cut the concentration in half, it's going to be 1/2 in the denominator, which is going to double the half-life. So each time you cut the concentration in half, the half-life doubles. All right, we'll move on to this one. If we're dealing with gases, then concentrations and pressures are directly proportional to each other. So we could use pressures here instead of concentrations. The partial pressures will be free. And so for gaseous reactions, this might be easier to deal with than concentration. And so this would be what order? This first order, second order? This reaction must be
You said right now each time you put the concentration in half, the half-life doubles?
Yeah, so if we make this 1/2 the original, then it'd be K times 1/2 and flip invert it. Each time we make it 1/2 the original, it'll double the half. This reaction, this is a single reactant going to multiple products. The multiple products, we don't worry about that. We just have a single reactant. That's important because then the reaction rate only depends on the single reactant in this concentration. And so this looks like to be first order. Can you see this has got to be first order because of the equations that they use here. It's first order. It might not be, we don't know if it's going to be first order, zero order, or second order. We have to determine that first, then figure it out. Here's how I draw a first order curve. Drawing a first order curve is easy if you draw it by half-life. The half-life is fixed on the first order. This is exponential decay here. This half-life is 80 seconds. You see that here. So every 80 seconds. This is decomposition of T-butyl peroxide. And decomposition of T-butyl peroxide, this looks to be peroxides are very unstable here. This is oxygen, single bond. Looks like it forms acetone. This is an ethane. The decomposition. Well, when we characterize reactions, oftentimes it's much easier to visualize this in terms of half-life. All radioactive decay processes are first order. And so if you just look at these first four, these are all radioactive decay. This is U-238. U-238 has a half-life of 4.51 billion years. And so let's just imagine this curve here being the radioactive decay of uranium. For uranium, we usually don't have the molarity for that. Usually for uranium, we just have the number of nuclides. So it'd be the number of nuclides up here and the number of nuclides down there. And so here, 4.5 billion years, you're down to half. 9 billion years, you're down to a quarter. And so usually, how many half-lives does it take to get to about, what nuclear chemists like to do is they like to go to about 90 to 95%. If 90 to 95% of it is decayed, then they say it's pretty much decayed. And typically that takes about 5 half-lives. 5 half-lives to, it'll take infinitely long to get rid of all of it, right? But about 5 half-lives you got the bulk of it. And so, well, we could figure it out, just by doing simple calculations like, we start off with 1, we end up with 1/2, and then we'll end up with 1/4, then 1/8, and then 1/16. 1/16 is what percentage remaining. So let's figure out, let me just do that. 1 divided by 16 is about half. 1 divided by 16. It's about 6.25% remaining. This is about 6.25% left. So here we have 100%. Here we have 50% is the remaining. This is reaction, and so 0% reaction, 50% reaction. At 1/4, this is 25% remaining. That means 75% of it is reacted. At 1/8, actually 1 divided by 8, this would be 12.5%. Actually, I didn't need to do the calculator for that. This is half 25. So this would be 87.5% reaction. This would be 93.75% reaction. And so actually, how many half-lives is that? 1, 2, 3, 4 half-lives. For 4 half-lives, we get about 94% of it was reacted. And so if we go with 5 half-lives would be 1/32. And so 1 divided by 32 would be half of this, which would be 3.5. And so after 5 half-lives, we have about 96.8, 96.9% reaction. And so this is greater than 95% reaction, so a lot of nuclear chemists will say, okay, that's decay. There's only about 5% left. How about 99%? Let's say I'm not happy with 96%. I want 99%. How long would it take to get 99% reaction? Well, there are 2 ways we could do it. We could do it qualitatively, that is by how many half-lives, or we could do it quantitatively by doing the prediction. And so I want in fact, I don't want just 99, I want 99.9% reaction. If I want 99.9% reaction, then you know what? This half-life is turning out to be kind of a hassle, because this will be 1/64th, which would be half of that, which would be, what's half of that? 1.5, 6, whatever. And so it's not quite 99.9%. It'd probably just be easier just to do a quantitative calculation. That is, at 99.9% reaction, how long, would that take in terms of so 99.9% reaction? Well, I could try to figure out the time required. Depends on the K value, of course. And so 99% reaction U-238. Well, the K value for this, well, actually, we don't know the K value. We know the T1 half. The T1 half for this is 4.5 times 10 to the 9th years. What was it, 4.51? Actually, the K value is here, but I'm not going to 4.51 times 10 to the 9th years. That's the T1 half. And therefore, K is equal to 0.693 divided by T1 half. This comes from the T1 half equation for first order. And so this is 0.693 divided by 4.51 times 10 to the 9th years. That 1 is important because that 1 is actually how many? That 1 needs 10 million years, so I don't want to round that off. 10 million years. And so, can you finish this calculation for me? How many years would it take for 99.9% of your future reactor? you get the years? How many years? No? So it's first order, so ln of a times t over a times 0 is equal to minus kt. And so for something like uranium, like I said, we don't normally think in terms of molar concentration. We usually think in terms of just do the pen. In terms of the activity. And so the a times 0, we're going to have how much left over. And so this is the amount remaining. So this is going to be ln of, we're going to have only 0.1% or 0.01 of the original remaining out of the original that we started off with. So the original amounts cancel out. Then you plug in your k here, your t, and we solve for the t. And so what do we get here? Skipping some steps in the algebra. I'll get the natural log of 0.01 divided by k. Divided by k would be times 4.51 times 10 to the 9th years. Divided by 0.693. Does someone have it?
Yeah.
What did you get?
I got for time? Or
Yeah.
for K? For
Time.
time. I got 2.997. It was 10 to the 10.
10 to the 10
Yeah, that's what I got.
years. Did anybody else? You got the same? Okay. So about 29.97 times 10 to the 9th years. So if this is about 5, this would be about 6. 6 times that. That's about 6 half-lives. Or together. Okay. All right. Then what we can do is we can see, you know, the reactions range from very slow, like uranium decays, very slow, 4.5 billion years, to much faster, like iodine, radioactive iodine, 8 days, you know. And so for the iodine, they're talking about, well, 5 half-lives, you know. The activity of the iodine should be way, way down to 5. And so iodine, radioactive iodine, this is like from like the nuclear meltdown or something like that. So you'd be concerned after the meltdown for about 5 times 8. You have 40 days. It's going to be quite high. But still, it's around. Sucrose, hydrolysis. This is hydrolysis of sucrose is 8.4 hours. However, if you have an enzyme, they have enzyme sucralase, then that time goes way, way down. And hydrolyzed sucrose very rapidly. Sucrose is what they call a disaccharide. It's made up of glucose and fructose. Break those. These are monosaccharides here. Ethylene oxide, here in this reaction, decomposition of the redox reaction here. 56.3 minutes. This is very fast. This is acetic acid. Hydrolysis. This is actually acetic acid hydrolysis. 10 to the minus 7 seconds. Very rapid. Was this second order? second order reactions. It's a rate law with the sum of the exponents. This is not exactly correct. You know, when we have the rate law with the sum of the exponents equals 2, yes, it is second order overall, but it's not necessarily second order in A. You know, well, it could be, you know, first order in A and first order in B. Depends on how many reactants you have. So this is what they're doing, is mixing it up here. This is multi-reactant. This is single reactant. When we have single reactant, then it's easier. We have multi-reactants, then, you know, we don't know what M is, and we don't know what N is. Those are two unknowns. So we have that same situation happening in lab. The rate law is going to be second order. That is, if we double A, it quadruples. And this is the integrated rate law for that from calculus. So this is all the empirical stuff. This is the plot of 1 over A versus time, straight line, linear, intercept there. This is the half-life equation here. The half-life equation is, well, something happened, I'm missing K in this half-life equation. It disappeared, and so this half-life equation is not correct. I just downloaded this. But anyway, you should always verify the equations. Even in lecture, you know, you should verify the equations. This is what we just derived. We have pseudo first order. This is what we did in the lab. You know, so when we have two reactants, we hold, this is what they say, hold one or more reactants constant by using high concentrations. Use the low concentration of the other reactant under study. And so here we have two reactants. And the reactant, we hold water very high. Water is 55.5 molar pure. So water won't change appreciably. And so the reaction appears to be first order because the water doesn't change, but in reality, the reaction depends on both the water and the other reactant here, which is this is called an ester. So here's a little summary. This is all empirical. You know, this is all just analyzing the data and coming up with an empirical equation to describe this. So here's the this. Now, what we got going here is this situation where can we make graphs? You know, for example, during a test. And how accurate would those graphs be? Can you calculate R squared by hand? And the answer is no, this is too much. And so the easiest thing to do is, well, what do we do? You know, what we do is we'll just have to do a manual determination of it. And so let's look at master. All right, so we'll take a look at, actually, let's see. How many points do we need to define a curve? Obviously, the more points we have, the better, because that means we don't have to worry as much about random error screwing things up. And so to define a curve, well, we need 2 points to define a straight line. So how many points do we need minimum to define a curve? Three points. And so we're going to need a minimum of 3 data points to determine the kinetics of a particular reaction. Now, what's better, 3 points tightly spaced or 3 points widely spaced? What do you think would be widely spaced? Because then, you know, if you take 3 points right at the beginning, it's hard to tell, you know, because if we're just looking at right at the very start of this, you know, is that 0 order, first order, or second order? You know, but if they're widely spaced, then it's obvious, you know, if a point comes out here versus here, you know, we can tell quite a bit easier what it is. And so we need a minimum of 3 points, but the more the better, because the more accuracy we'll have, the more points. And the wider the spacing interval, the better. But a minimum of 3 points to define curve. And so what we're going to do is we're just going to take those first 3 points there. So, you know, if we look at the time, it's 0, 200, 400. And then we look at the concentration, in this case of the hydrogen peroxide, it's 232, 2.01, 172. Now this is easy to do if we have a computer. If we have a computer, we'll just graph it. Well, we're done. But if we don't have a computer, how do we do this? How we do this is this. We do what I'm going to call is a K analysis. For K analysis, K is the slope of the linear line. So what we'll do is we'll do this. From 0 to 200, we'll call it K1. And from 200 to 400, we'll call it K2. So we're looking at the 2 intervals here. And so in K analysis, we look from 0 to 100, we got K1. And then from 200 to 400, we have K2. Now K2 might be the same, like this, or it might be different. You know, it depends on what, if it's the same or close to the same, we'd say it's linear. If it's different, we'll say, well, it's probably nonlinear then. And so we're going to do this. For 0 order, K, we solve that equation. K is going to be equal to A times T minus A times 0 divided by T, the time interval. We'll take care of that. So what we'll do is we'll look at K1 and then compare it to K2. So K1 is 200 minus 0 and, oops, that's the time interval. It's going to be A times T, actually this is minus. So it's a minus. It's going to be 2.01 minus 2.32 divided by the time interval, which is 200. This is a molar per second. So that's going to be 31.31 divided by 200. .00155 molar per second. Okay, then we look at K2. Let's see, is it going to be the same slope or is it going to be a little different slope? And so if we look at the next time interval, this is going to be minus, and so 172 minus 2.01 divided by, the time interval here is going to be 200 seconds again. It's going from 200 to 400. And so this is going to be 0.71 divided by 200. We have 0.71 divided by 200. And this gives us 0.00355 molar per second. So are the two slopes the same? No. In fact, sometimes they look, well, I don't know. What we should do is we should calculate the percent difference in the case. The percent difference is usually you pick the biggest, well, we only have one, so it's biggest minus the smallest, divided by the smallest, times 100%. And so if I look at the percent difference here, I take the biggest, 0.00355, minus the smallest, 0.00155, divided by the smallest, 0.00155, times 100%. So, and this is 129% difference in the slopes. 129.0% difference. This is a huge difference in the slopes. So it's not looking good for zero order because zero order doesn't really, it should be, you know, the slope should be the same. K should be linear. Now, for first order, you know, K should be constant. If it's first order, K should be constant when it's plugged into this equation. A times T over A times 0 is equal to minus KT. So we solve for K. K is equal to minus Lm of A times T over A times 0 over the time interval here. And so let's look at K1, the first slope here. K1 is going to be minus Lm of A times T, 2.01, over A times 0, 231. 232, divided by the time interval. Time interval is 200 seconds. Now, the A naught is just your starting, wherever you're starting. So, so let's go 2.01 divided by 232. Not necessarily times 0, but the natural log of that divided by 200. And I get K1 is 000, 7171 seconds to the minus 1. And so the units are different. K2, let's take that next time interval. Ln, okay, it's going to be 172 over the start. The start of this second interval will be 201, so that's going to be my A naught. Divided by the time interval, 200 to 400, it's another 200 seconds. So I'm going to go 172 divided by 2.01. Take the natural log of that, divided by 200. I get 0.000779. 7790. So I guess the minus 1. So it looks off, you know, 717, 779. It doesn't look like it's the same, right? But let's go ahead and we're going to calculate the percent difference here. And so let's take the biggest, which is going to be 779. 779 minus the smallest, 717. Divided by the smallest. Times 8.6. 8.63%. Well, let's go to second order because this doesn't look so good. In fact, we ought to try all of them because we don't know, you know, or how dramatically different they might be or similar. And so if we assume it's second order, Then the second order has this equation, 1 over 8 times t is equal to plus kt plus 1 over 8 times 0. And so if we solve for k is at 1 over 8 times t minus 1 over 8 times 0 divided by t. Time interval. So this is k. And so k1, the first interval here, is going to be 1 over 201 minus 1 over 232 divided by the time interval 200. And the units here are molar to minus 1, seconds to minus 1. And so the way I'll do this is I'll do 2.01 invert minus 2.32 invert equals divided by 200. Triple 0, 3, 3, 2, 3. Okay, molar to minus 1, seconds to minus 1. Okay, let's look at the second interval here. The second interval is going to be 172, and 201 will be our start, and it's 200 second interval. So 172 invert minus 2.01 invert equals divided by 200 equals 0.004194. And so let's do this one. As far as percentages go, it's going to be 4194 minus 3323 divided by 3323 times the 100, which gives me, if I did this correctly, 4,094%. And so which one is the most constant K? First order. But really there should have been 0% difference in the slopes, right? But it turns out it's not necessarily, because of, random error that could occur, or maybe I made a mistake, because this looks pretty spot on. I could have made a mistake in my calculation. But we would do that. Okay, and so this tells us it's forced order, and then we would get the average K. And so we get the rate law like this. The rate is equal to K average. So the average of the two K values from that, and that's going to be hydrogen peroxide to the first. The problem is we're only using 3 data points. They use a lot more data points in there. And so the K value that they're going to get is much better than our K value that we get. Because they were just using more data. I mean, in general, it could be the same because if you get lucky, because random error could cancel each other out. It's likely it's, All right, so I erased the numbers here. We just average this. K1 plus K2 divided by 2 for first order. Okay. All right, that's what to do if you don't have access to Excel. You'd have to do it manually. Now that is empirical analysis. And we can make predictions, how long, how much, after let's say after 30 days, how much do you have left? Well, we just plug that into the integrated rate law. We'd have to have initial. Or we could do a percentage, After 10 years, how much decayed or how much is left over. And so those are typical problems that we have, calculations. That's for single. If we have multi reacting. We're just looking for the rate law, what happens at rate. Now the next part of chapter 20 deals with theoretical models, with theory. And so where does the order come from? Is zero order, first order, second order? What's the origin of M and N? So far the only way we can determine M and N is by experiment. But is there a way to predict what M and N should be based on theory? And so, we can always do the experiment and figure out what M and N are, but it turns out there is a way to figure out what M and N are based on theory. And the theory is how things react and how things react. We look at collision theory. In kinematic molecular theory, way back in the gas chapter, there was something called the collision frequency. How many collisions happen per second. In gases, the collision density or the collision frequency is 10 to the 32 collisions per second. 10 to the 32 collisions per second is huge. If you had 10 to the 32 collisions per second, well, that's more than a mole's. That's more than a mole of collisions per second. 10 to the 23 would be a mole of collisions. And so the reaction rate should be more than a mole per second. More than a mole per second. Have you seen anything react that fast? Probably not, because it would be pretty explosive at a mole per second reacting. What it turns out that even though there are 10 to the 32 collisions per second, and if they're 10 to the 32, if each collision produced a reaction, the rate would be 10 to the 6. Well, I got to figure out how they did that. Well, I guess you got to look at more than one molecule. If you look at all the molecules as a whole, we're looking at 1 million moles per second. Can you imagine something reacting at 1 million moles per second? Impossible. I mean, that would be incredibly fast reaction. In reality, the actual rates are 10 to the minus 4. 10 to the minus 4 would be what? 10 to the minus 4 would be like a tenth of a millimole or 100 micromoles. 10 to the minus 4 would be 100 micromoles per second. 100 micromoles, now that is a lot slower. And so the end result is only a fraction of the collisions actually lead to a reaction. And so in collision theory, what makes a successful collision? Well, there are two things that make a successful collision. One, it has to have enough energy to break bonds. And two, it has to be of the correct orientation. And so here, this is a little bit out of place here. Let's look at orientation first. And this is a favorable orientation where we have nitrous oxide, N2O, reacting with nitric oxide, NO. And oxygen and nitrogen have to be pointed towards each other in this particular reaction. And so we have a collision which breaks the bonds and forms new bonds, and we end up with NO2 and N2. However, if the two O's collide with each other, then we don't have a successful reaction there. Or if the two N's collide with each other, we don't have a successful reaction there. Plus, they can come at angles too. They don't, it's not going to be a head-on collision. And so, one, we need the proper orientation. But if the collision's very light, like a parking lot, fender bender versus a heavy collision, like on a freeway, a very light collision here, a very low energy collision might not, even with the correct orientation, might not result in reaction because you just don't have enough energy to break the bond. We need enough energy to break the bond. That energy, the minimum amount of energy required, and it's not just bond breakage because there's bond formation happening at the same time. Bond breakage costs energy, bond formation releases energy. So the actual energy involved is a little less than the total energy to break the bonds. But that energy is called the activation energy. And so the activation energy is this kind of minimum. The activation energy is shown here by this black arrow. This is the minimum energy required to break the bonds and to form the new bond. And so any molecules, this is a population map. You've seen this population map before many times, I think. Maxwell-Boltzmann type thermal distribution population. The red one's higher temperature, the blue one's lower temperature. But what we can see is there's going to be a cutoff energy. This cutoff energy, all the molecules above this cutoff energy have enough energy to break the bond. All the molecules below, now that's the bulk of the population. Especially, well, at higher temperatures, you can increase the population of higher energy molecules. But this is called the activation energy. It's cut off. Now, if the bonds are very strong, the activation energy is much higher. If the bonds are very weak, the activation energy is much lower. So, weak bonds reacts fast. They're much more reactive. Strong bonds are going to react slow because of the activation barrier. Okay, so now this is kind of backwards. If the activation barrier is high, only a few molecules have sufficient kinetic energy and the reaction is slower. As temperature increases, the reaction rate increases. Orientation of the molecules, orientation of the molecules is important, unless they're, unless this hydrogen has no orientation because it's spherical. It's not so important there. And so, let's go back over here. For a reaction to occur, there must be a redistribution of energy sufficient to break certain bonds in the reacting molecule. This is called the activation energy. The minimum energy above the average kinetic energy that molecules must bring to their collisions. In other words, activation energy is what we need to get these to react. That's one way of visualizing the activation energy is based on the population. The other way of visualizing the activation energy is based on this. This diagram, what is this diagram called, this plot? This plot is a plot of potential energy, or energy, on the y-axis. And then on the x-axis, we have something very funny. The x-axis says reaction progress. Reaction progress means this is what we have at the beginning, and this is what we have at the end. And so we're following the progress of the reaction. This plot is called a reaction profile. And so the reaction profile takes us from the beginning. The beginning is the reactants, nitrous oxide and nitric oxide. And they got to collide. They got to collide with the right orientation and right energy. That energy is shown here as an energy barrier. Overall, this reaction is exothermic. If you look at delta H, it's minus 139 kilojoules. But you have to invest money to make money. So if you want this 139, you have to invest more than 139 here because the activation barrier is quite high. And so nothing's going to happen in this unless you invest that initial energy here. And so basically you got to go over this activation hump, which is breaking bonds. Actually, it's breaking and forming bonds. When we're breaking and forming bonds, this is called the transition state here. The transition state is a state in which the bonds are being broken and the bonds are being formed here. So we're breaking this bond here, we're forming this bond here. And so it's not just breaking. Okay, and then the transition state has two ways. It can fall back down, that is reform this bond, break this bond, or it can fall this way. If it falls this way, it's favorable. And we're going to form NO2 and N2, the products here. And so the activation energy here is 209 kilojoules per mole. You see that E sub A is the symbol that we give. And the hill that you have to climb is quite high, 209. It's not just a downhill ride, even though overall it's exothermic because 209 up and then 139 down gives us 139. This reaction is not so easy to reverse because to reverse this we have to climb this big hill, which is 348. So the activation and barrier in the reverse is really tough to encounter. This one's a lot easier. Okay, we're out of time, so we'll continue with the theory next time.